and welcome to Unit 4. We will be starting with energy, thermodynamics, enthalpy, and calorimetry. You might think that there's a little bit of review here, but not so much. Energy is going to be taking a big left turn into abstractionville, while occasionally dipping its toes into really concrete stuff. I'll do what I can to keep it grounded and explicable for you, but you're going to have to strap yourself in and get ready, because it's going to be tough. So we've already discussed energy a bit, but now we're going to talk about it in more of a how can we put it to use sort of way. The 19th century was big on practical applications. That's when thermodynamics first started. Thermodynamics, in order to study something, breaks the universe down into two pieces, the system and the surroundings. This here is the system, the object under consideration. And everything else in the universe is the surroundings, whatever it is you're not studying. The system plus the surroundings is the entire universe. Okay. Considering everything is the universe. The system is what you care about, the surroundings are everything you don't care about. You have to pay attention to this divide. You have to think about it in these terms because you need to consider the system in terms of the surroundings. They interact with one another. The system can lose heat to the surroundings. The surroundings can do work on the system. Or maybe the system loses a significant amount of material to the surroundings. When you study thermodynamics, you have to think about these things in terms of their interactions. You're also going to end up with a lot of really nasty math. I will do everything I can to shield you from that. I won't be entirely successful, partly because you can't discuss it any other way. Remember, kinetic energy is the energy of motion, the energy of an object in motion. Okay, the faster an object moves, the more kinetic energy it has. The more massive the object, the more kinetic energy it has. But the motion, the actual speed, is more important than the mass. An object at rest has zero kinetic energy. It's just sitting there, no kinetic energy. But if the object is in motion, then it's going to have a positive kinetic energy greater than zero. So with that in mind, let's discuss the differences and some of the similarities, I suppose, between temperature, thermal energy, heat, and kinetic energy. These are all tied together in many ways. We'll actually be starting with thermal energy. Thermal energy rather than temperature because it's actually more central, even though we've dealt with temperature before. Now, thermal energy is the energy associated with the system that you find that results from, that is stored in the random motion of the particles of the system. No matter what system you're talking about, whether it's a solid, a liquid, or a gas, all of the particles contained within it are in constant random motion, always in every direction you can conceive of, bouncing off one another. Even the particles of a solid are always in motion. They're always vibrating in place. They're not really going anywhere, but they're still in constant motion. This means that as you add heat to any system, regardless of solid, liquid, or gas, the particles within that system are going to move faster. They continue randomly moving around, running into one another. For a solid, remaining in place. For a liquid and gas, moving freely, but moving faster. So the higher the thermal energy of a system, the hotter it is, the faster the particles are bouncing around inside of it. When it's cold, those particles are moving more slowly. Now let's go ahead and hop on over to temperature. Temperature is not the same thing as thermal energy. That's why we give it a different name. Temperature is a measure of thermal energy, not thermal energy itself. On the one hand, your thermal energy is actually the sum of all of the random motion of the particles. This is the Greek letter sigma. Sigma is used to mean the sum, the addition, the total of what follows. And thermal energy is the sum of the random motion of all of the particles in the system. Temperature, on the other hand, whether it's measured in degrees Celsius or Kelvin or degrees Fahrenheit, is proportional to the average kinetic energy of the system. This sign here in the middle looks sort of like a swoopier alpha, means proportional. It means that as kinetic energy goes up, temperature goes up. As kinetic energy goes down, temperature goes down. And the angled brackets around kinetic energy mean that we're talking about the average kinetic energy. Another way of writing that would be kinetic energy with a bar over it, but personally I prefer the angled brackets. So temperature is proportional to the average kinetic energy of all the particles in the system. We consider temperature most of the time rather than thermal energy because thermal energy is difficult to measure directly. When you're talking about a mole of particles, a near infinity of particles, it's really very difficult and pretty much impossible to measure their thermal energy, their kinetic energy of every particle. But if you measure the temperature, you're just sticking a thermometer in there, you're getting the average, and it's very easy to measure directly. You don't have to look at every single particle, you're looking at the system as a whole. Moving forward, let's move on to heat. Heat is represented by the letter Q, which is kind of a problem because we've already used the letter Q to represent charge. Remember, an electron has a charge of -1, so Q equals -1. A proton has a charge of +1. And finally, the neutron in 0 has a charge Q equals 0. But when you look at it, there's only so many letters in the alphabet, and this won't always be the case. Sometimes Q represents charge, but here in thermodynamics, Q represents heat. Yes, this is difficult. Yes, you're going to hate it. Yes, you're just going to have to get used to it. So here in thermodynamics, heat is Q, is the movement or transfer of thermal energy from one location to another. It could be from inside the system to the surroundings, from surroundings to system, from one place in a system to another, and so on. There are 3 ways for heat transfer to occur in any given system: conduction, convection, and radiation. Conduction is rather straightforward. The 2 objects are just in physical contact with one another. They're touching. And you'll get transfer from one to the other. One side of our system is at a high temperature. The other side of our system is at a low temperature. And heat will move from high to low until the temperatures of the 2 halves are equal. Very straightforward. Next up, hopefully also familiar, we have convection, where conduction is the transfer of energy from one object to another. In convection, the matter itself moves from one location to another. You'll have seen this with the heat shimmer above a fire or flame, when the air is moving upward, or even a hot air balloon rising up into the sky. So, to reiterate, conduction is just the movement of energy from one location to another, but convection is the movement of matter from one location to another, which brings its thermal energy along with it for the ride. And finally we have two systems that are completely isolated from one another. They're not in physical contact, so no conduction is possible, and there's no way for matter to get from one to the other, so no convection. So you have one at a high temperature, one at a low temperature. They will eventually be at the same temperature. The question is how. And the answer is radiation. Luminous beings are we. Okay, Yoda was actually babbling on about space Taoism, but he was kind of correct. We are all glowing in infrared. Some things are glowing in visible radiation. Now, over here on the left, we have the hot thing glowing hotter. It's giving out more radiation than it's receiving. It's going to cool down. The cold thing is glowing cooler. It's giving off less than it receives, so it's going to warm up. And eventually the two will be at the same temperature. And so those are the three different ways that heat will go from one place to another. Radiation of electromagnetic energy, convection, where matter moves and carries energy with it, and conduction, where the heat just moves directly from one object to the other. Now, that said, we don't really care, mostly, about how heat is transferred from one place to another. That's mostly because we have simplified our systems over and over and over again, until we can eliminate most of the math, most of the physical realities about it, and just get to a set of conditions where it's really easy to think about heat. Now, the system cares, of course, and it'll matter to experimental setups, but not so much to the math. In the end, conduction, convection, radiation, they all boil down to Q. So that is temperature, thermal energy, and heat. Thermal energy is all the kinetic energy inside of a system. Temperature is the average kinetic energy of the particles inside the system, and heat is the transfer of thermal energy from one location to another. And of course we have potential energy, energy that is in some way stored. For example, gravitational potential energy is energy stored in the warping of space. Space is warped when two objects are separated physically. Electrical potential energy, electric charges warp space in a different way. Magnetic potential energy, space is warped in another more different way, and so on. Elastic potential energy, when you stretch a rubber band, pull back a bowstring, or stretch a slinky, you're going to get potential energy stored in the physical structure of whatever matter you're twisting or bending or compressing or what have you. But in the end, everything flows downhill. Potential energy wants to be minimized, wants to be in the lowest possible potential energy state. Everything will eventually go to the lowest form of energy, heat. We often put this in terms of a potential energy landscape. We draw a graph and we plot it out. So if you were to plot height versus, say, x, the distance from your front door to another location. As you travel along, you see it goes up, it goes down, just reflecting, your height, say, above sea level at any given, distance. So as you get further away, it's going to change based on the ground. So here it's high, here it's low, and you've just mapped out a one-dimensional landscape. But you can do the same thing with other quantities, other factors and variables. Instead of height, you could talk about the electric field around an object. Instead of distance, you could talk about the angle that you're making with the object. Or you could talk about the distance from the object. Either way, you can still get a potential energy landscape. And, of course, the laws of the universe say that potential energy needs to be minimized. You're always going to roll downhill. Now, sometimes these potential energies can come into conflict. Say, if you balance a magnet above another magnet. The gravitational potential energy needs to be minimized by falling down, but the magnetic potential energy needs to be minimized by falling up. So they're going to have to find a compromise, a balance between the two. Because if you get closer to the magnet, you're raising the magnetic potential energy. If you're getting further away, you're raising the gravitational potential energy, and so on. So eventually it'll stop. It'll find a balance, a halfway point, somewhere in between the two. And that explains what may be a familiar sight to you. If you have two posts with a rope hanging between them, let's go ahead and throw some grass here around the base, and a dog sniffing at the post, getting the news and getting ready to take a pee. And in between these two posts, you have, say, a rope or a chain hanging. It's going to make this little shape here, the curvy shape. It's called a quaternary. And why does the rope hang like that in that particular curve? Why doesn't it go make a straight V, down to the bottom? Why doesn't it go straight across, then down, then over, then back up? The reason is that any deviation from the quaternary curve will raise the potential energy. The quaternary is the form, the shape that minimizes potential energy. Any deviation from that will raise it. Even a little bit is bad. It has to minimize the potential energy, and that curve is how it does so. And that is where we'll go ahead and end this lecture. When we come back, we will continue with our intro to thermodynamics. Probably not quite so many peeing dogs going forward.